Oh, sorry, we have the integral gain, derivative gain, and the proportional gain labeled as what Ki, Kd, and Kp. Then we need for differential, we needed to keep track of what? The current error, that is the error at the time the correction is being made, and then the previous error. So that the difference between gives us what? The change in error. So we needed a variable to store the previous error and then the error, which is the current error. Are we there? Then for integral, for us to be able to do integral control, what did we need? We needed to do an accumulation, or we needed to store an accumulation error over the entire duration when the program was being executed. So we have an integral error variable. I follow it. So we have an integral error variable, and then we have an integral gain, which is used to scale that integral error. Initially, it should be set to 0. I'll do that. Good. Now, after these variables have been defined, then our program begins its execution. What is the first thing we do? The first thing we do is that the program will have to first of all know the error, which is the deviation from the standard, or the deviation from the normal thing that should happen. So how do we get that error? The light sensor records its value, which is supposed to be 50 if our robot is directly in between the black and the white. So it records that value, and we subtract what? 50 from it. Subtracting 50 from it gives us what? The difference between the desired value and what? The actual value. The result is the deviation, how far we have deviated from our desired location, or the error. So we store that result as what? The error, into the variable that was created as error. So we store that as what? Our error. Once we know the error, it is that error that we want to compensate for, or we want to correct. So what do? We say that we don't want to use the entire error to effect the change or the correction, because the error value is large. It can be as large as 50, because the maximum value for the light sensor can be 100, which means our actual value can be 100, and our desired value is set to 50. So we can have an error value of what? About 100, or we can have so let's say an error of about what? 50. But we don't want to use this whole 50 to effect the correction, because we saw the effect. It was quite drastic. 50 will be, if our default speed was 50, then we'll be driving at what? At 100. Are we there? So we have a default speed that we will effect to the motors, or the motors are constantly moving at a default speed, which I think was shown in one of the early variables that had been defined. Let's go back and see that. So we have the variable here labeled what? Default speed, which was set to 25. And that is the speed that automatically controls the motors if there is no error. So if we allow the maximum of 50 to happen, it means we'll be driving at 75 when we have the maximum error. And remember, at that 75, one of them is going reverse by 75, and the other is going forward by 75, and that will spin your robot. So we did not want that to happen. So we say the error value that has been calculated and stored. So from here we say the error value that has been calculated as what? Light sensor minus 50 stored as error. We pick that error value and scale it down. How do we scale it down? We scale it down by multiplying it with what? The proportional gain. So error times proportional gain. Proportional gain goes to A, error goes to B. The sign is what? Multiplication. So it multiplies it. And because proportional gain is a fraction, it scales your result down. So the result here is what we call the proportional output. Proportional output. But for PID control, we want a proportional output, a derivative output, and then an integral output. The three combined will give you your PID output, which will control your process or your movement. Are we there? Good. So there is our proportional output coming from what? From this. Let's move on. So, with our proportional output coming from here, we also need our derivative output. How do we get our derivative output? Derivative output is calculated as what? The derivative itself is the rate of change of error. So the previous error and the current error will have to be subtracted. So we have what? Our previous error coming from where? Here as what? P. And then we have A coming from, it goes to where the error was calculated. So error minus previous error will give you the change in error. Are you following? Then we multiply that by what? The derivative gain. So you can see C is derivative gain. So we have A minus B all times what? C. So the output from here is what? Our derivative output. So derivative output. Are we there? So derivative output is also coming from this computation. Then we need the last control, which is the integral output. And that is our integral error. That is the accumulated integral error times what? The integral gain. So let's see how that also came in. I decided to use it because I wanted to report that we missed that one and I wanted to keep that so we can share and use of it. I'm happy. Sorry for that, but I have to do that. But I need to do this so that next time when we need it, we can reference it. So last time, we want to do proportional of PID control, which is proportional derivative integral control. To do that, so you have to make your mix. So we have three control variables, which are what? Our integral gain, derivative gain, and the proportional gain. The proportional, derivative, integral. Now, outside this, what does proportional mean? Proportional says we are controlling the process. There is an error. Based on the error that has occurred, take a portion of that error and use that to effect your control, so that you can bring your process back on track. So for your proportional gain, it is meant to control the error that has occurred at the point where your control or your correction is being made. Then there is a derivative gain, which is a predictive factor. What derivative output? What derivative output says is that if I know the change of error, the rate at which the error is changing, I can predict the next error. For that to be possible, it means we must be able to tell the difference or the change in error. And to be able to tell the change in error, we need to know the previous error and then what? The current error. Subtracting the two will give us the difference or the change in error. Are we there? So we have enough variables to give us our derivative output. Once we know the change in error, the derivative gain is used to scale it up. And we said we are scaling it up by a factor, you can see a factor of 10 because and the first, at one iteration, the error, assuming the error is 8. Because of the clock speed of your processor, at the second iteration, the error is likely to be, maybe, let's say the first one was 8.0014. The next error might be 8.0013 or 12. And you can see the change in error is what? 0.0012. Oh, no, 02. I'm following. This is so minimal that if you want it to have any significant impact on the correction, you want to scale it by a factor of about 10. I'm following. Or about 100. If you scale it up by a factor of 100, it becomes what? 0. What? 00 what? 0.02, right? So you can see that your derivative gain rather goes in what? Tens, hundreds, and thousands if you want it to have significant impact. I follow you. But for error, error of 8, if you want to correct with the whole error, I follow. If, like, let's say your current error, which is 8.04, if you want to correct it by the whole error, it's quite large. So you rather want to scale it by what? A fraction, which is like 0.5. You say, no, let's use half of the error for what? The correction. I get it. And that is why your proportional gain is a fraction, but your integral gain, your derivative gain is what? Multiples of 10 or larger numbers. Are we there? Good. Then there is a third bit, which is the integral control. The integral control says we want to accumulate all the errors that have happened in the past and use that to effect some form of correction. So we also introduced a variable called like the integral error, and it will be scaled down by what? The integral gain. You can see the value of integral gain is also very small, about 0.00, maybe 0.1 or 0.05, something like this. Because accumulating the errors become what? Large. So you want to scale it down far down. So the first error was 8 point, the second error is 16.0026. The next error, so as we execute the error one, the integral error expands. And we want the integral gain to scale it all the way down. So I made mention for some industrial processes, after some duration of operation, the integral error is wiped off and we start on a clean sheet again, because as the process goes for a long time, the integral error accumulates and is likely to become a noise rather than what? A corrective mechanism. So these are the variables we created and thought they will be useful. So quickly, let's go through how they are used. So it's not my fault. It's not my fault. The thing wasn't recorded because because my kid did not think the memory card is better. Or you are recording. Okay, I'll take it. It's your phone that so what we have now is to say that first step is to know the error, because almost all the corrections depend on the error. So to know the error, what do? We say the line senses current reading. We subtract what? The desired reading or desired value. This is what we want it to be. We want it to stay half on the white, half on the black. So we subtract that and the result is called as what? As error. The result is the deviation from the desired location. Once we store that as error, we want to multiply that by the proportional gain to scale it down like we said, as we said. So we do error times proportional gain, and the result is what we call our proportional output. The result is called our proportional output. So the result is called our proportional output. So with our proportional output coming out of this, the next thing we need to add to our corrective variable is the derivative output. How do we get the derivative output? We said it is the change of error, the rate at which error is changing. So we said what? Previous output or previous error minus what? So the current error, which is the error we have just calculated, it goes from that point, I follow it. And then we subtract what? The previous error from it. So we have A minus B. I follow. But after we subtract, we want to scale it. And we scale it by multiplying it with what? C. And as we said, we multiply by a factor of what? The derivative gain to scale it up. So that is our derivative output. Once we have the derivative output, the last bit is the integral output, which is the accumulated error over time. So we have our derivative output coming from here. To get our integral output, we take the integral error and scale it by the integral gain. So just multiply the integral output by the integral gain. I follow. And the output now comes as what? C. So this block here is adding our proportional output plus our derivative output So we have the derivative output, and then our integral output. This block has the three of them. So what we have coming out of here is what? So A plus B plus, that is our proportional derivative integral output added together. How do we use that to control? We add that corrective variable to the speed of one motor and subtract it from the speed of another motor. So we say the default speed, which we set to 25, plus that output should go to what? Motor A. And then that same default speed minus the corrective output, I follow it, should go to what? Motor D. But before we end, we say that before this round ends, the error that was used in this round should be stored for usage as the previous error in the next round. So the error is now fetched and stored as previous error. And the integral error should become what? The current error plus the already accumulated error, I follow it, should be added and stored back as what? Our new integral error, I follow it. And then it goes back to the beginning. So that is PID line following or PID control. Is that clear? Okay. So now let's quickly drive through some two-line sensor line following techniques. That is not difficult, so we'll be done very soon. Once you understood what you've done, all what is left is application of similar things. So, with two-line sensor line following, you have two light sensors which have been calibrated. So let's say you have one light sensor on port. Where's the other remote? The one that has two light sensors. Can you show your camera is good?
Can check. It's okay.
You sure it's dark? It's dark.
It's not right.
Continue.
It's okay. Don't worry.
You get home.
We'll do it because I don't want to finish training again.
I get black.
Don't worry.
I get calculator.
So we have this robot with two light sensors. Now the task is that unlike the first situation where we had only one light sensor, this time we want our robot to grab this line, I-following, and then as we navigate, we make sure that one of the light sensors stays on the right and the other stays what? On the left. That is easier. Why do we say that is easier? Because we could simply program a robot to say that you have two light sensors. Make sure one of them is always on the right, to the right, and another is always on the right to your left. So you have this. I'll use this to make it very easy. Okay, so this is what you want to have. You want to grab the line this way. Now, if you grab the line this way, there are four possible conditions. So the conditions are this: you have line sensor on port 1, let's say another line sensor on port 4. And then you have two motors to control. One on what? A and the other on what? On B. It could be the state that the line sensor on port 1 is on the right, and the one on port 4 is also on the right. What that means is that the line is in between what? The two sensors. So what do we say? We say if the value from the first sensor is greater than 50, I follow it, and this is also greater than 50, it means both of them are into the white. So what do? You move motor A at the same speed as D. So let's say A should drive at 30, D should drive at what? 30. If it happens to be the situation such that you have one of them on the black. So in a situation you have, let's say, let me take this one to be from the one light sensor 1 and light sensor 4. So if it is the case that light sensor 1 is having a value greater than what? 50 because it is on the white, and the left sensor is having a value less than 50 because it is what? On the black. Then the situation is going to be said that let me name this motor A and motor D. So what do I do? Which of them should stop?
D.
This is A, this is D. So D stops. So D should stop. And A should what? Move. I follow you. Then it will correct the robot by bringing this one back on track. If it is the case that we have this time, this one rather is on what? So let me say, let's begin to use black. I follow it. And then it's on what? On white. What is the action? A should do what?
Stop.
A should rather stop and D should what? Move. I follow it. And then we could finally have a case like this where both of them are on the black. We decide on what action to take. So let's say black and what? Black. So we decide to do what? Let's say stop and stop. Let's assume that's our finish line. So once we've written this condition, what we are supposed to do is not different from what we did. We are only controlling motors based on what? Conditions. I follow it. So how are we going to do that? The switch block allows us to take decisions. So I said we have we've calibrated the light sensor on port 1. We have to calibrate the light sensor on port 4. So quickly, we are going to take readings. Who will take readings for us?
Why you call my name?
Take readings for us.
For 2.
Take 3 readings and I record them. So Iva is taking readings for black and white. Okay, so black. 8. Come again. No. Make sure that sensor. What is the sensor on port 4? There are 2 sensors, so make sure that one is pointed to the black. 12. 14. Okay, now white. 83. Quick. 80. Take another one. It's too like far from. Okay, 80. Okay, so what's the average? What's the average black?
11.3.
11.1.
33.
33. Average white.
81.
81. Okay, so if we were calibrating this sensor, you all recall, I need a response this time because we've gone through once. So to calibrate this, what do? We were expecting 100 and 0, right? What did we get? We had 11.133 and 1? 81. So when we expected 100, we got 81. And when we expected 0, we had what? 11.33. That gives us this line. So we need what? The gradient, right? How do we calculate the gradient? Change the y over what? Change the x. So we have change the y as 100 minus 0. Change the x as what? 81 minus 11.33. And that gives us 100 over what? 100 over 69.177. 67, sorry. Okay. And what's that? 100 divided by 69.67, 1.1.
I don't get more second for this one.
435. Good. So we have our M as 1.435. Our C becomes what? We know the equation is y equals what? Mx plus C. So C is equal to what? Y minus what? Mx, right? So what do we say? If we pick one of the points, let's pick this point. This point is on the point what? 11.33, 0, right? So that becomes what? C equals 0 minus what? M, we calculated as 1.435 times what? X. The X at this point is what? 11.33. So we get C to be what?
Negative 16.25.
Negative 16.259. Good. So we want to build this equation y equals what? 1.435 times what? Light sensor minus 16.259. Right? Good. So we go through together. First thing we need what? A constant block to store. So we need a constant block to store what? A constant block to store the M, which is what's the value for M?
1.435.
1.435. It should multiply what? The light sensor reading. So times the light sensor reading. Are you following?
Yeah.
Our light sensor is on which port? You might want to take the reading.
I didn't check this.
It's on port 4. Then how did you take the reading?
I didn't check.
Light sensor is on port 4, and then we make it measure what? Reflected light intensity. So if we measure the reflected light intensity, we have to multiply it by the constant, which is M. So light sensor reading times 1.435, are you following? That has been multiplied. Then the result, what happens to it? We have to subtract our C, right? Maybe I should get this thing back to record part of the board. So our equation is as we have here. So we have multiplied 1.45 by the light sensor. We are subtracting the C from it. I pick another constant, right? I label it. I put the value at. What value will you put in there? 16 points. So 16.2 is it 95? 259. You are not speaking, so I can't hear you. So I change this. I can change it to advance, or say I need another math block. I set it to subtraction. So the result from this minus what? That becomes plus. So it has to, if I put negative 16 here, I get positive. So I have to change the value to positive 16.259. Good. Now, I have created this block. I'm going to create a mind block directly, what we did initially from this. So what do? I select the entire thing and say tools, mind block builder. So I'm creating my own block from that. So I say create a mind block from this. Label it P4 underscore, let's say CAL for calibration. Select what symbol you want to put on it. Give a description of the block you are creating. So I say a block to calibrate light sensor on port 4. Good. Then I will add a parameter. The parameter does this. Something will have to come outside of the block. After it works, it has to give us a value of y. Are you following? When you pick the math block, you can see it looks like this. There is this, there is that, and then there is what? This. Where you put A, B, and equal to. These are called input parameters. So they allow you to feed values in. And it is called output parameter because it allows you to what? To pick value out. So the block we are creating, it has to give us a value. So it needs an output parameter where it will feed that value out for us to use. So I click on the plus sign here, add parameter. Then under parameter setup, I can choose whether it is an input or what? An output. So I say this is an output parameter. And the type of output I'm expecting from it is what? A number. I'm following. I can change the parameter icon and say the label should not be A, but let's say Y. And then I click on finish. I've created the block. All I need to do is to say that this parameter I created, what value should flow out of it? The whole result from what? The calculation should flow out of what? Of that. So I have created a block, and that is how it will look like. Good. So for the logic we have gone through, to program that logic, this is what we say. If the robot wants to make any movement, what it has to do is to check from the right and check from the left and decide how it should move. I follow you. All our movements have been built out here. Once you check from the right and check from the left, you can decide whether we should go for it, we should stop this and move that, stop that and move the other. I follow you. So we say, check from your light sensor on port 1. Check if the value coming out of that sensor is greater than 50. So I pick the compare block, and we say you are comparing if it is greater. So I do this, compare if the value from port 1 is greater than what? 50. The result will be a true or false. What do we need? Just like the first one you did, a switch block to receive that and take a decision. The switch block this time depends on what? A true or false value, which is logic. So the logic from this thinking should be fed to the switch block to decide on what to do. But we are saying that if you check from port 1 and it's greater than 50, it is not enough to take an action. You need to check from port 4 as well. So we say within here, also check from port 4. I follow you. If the value from port 4 is also greater than 50 or not, I follow it. So again, I say check if it is also greater than 50. I follow it. If it was the case that, so what this means